as measures of central tendency. And we'll get to that momentarily. The first thing I want to do, however, is to take a very quick look at those problems that you were set last time, dealing with frequency distributions, proportions, percentages, and ratios. The answers to those problems are now available on WebCT under the label Assignment 1. If you work through those 90 scores, you should have generated a frequency distribution that looks like the one that we had in class last time, going from 0 to 52. You should have discovered that there were 6 zeros, there were 2 1s, there was a 2, there was a 3, there were 2 6s, and so on, through to there being 4 52s and a total of 90 scores. And that was simply a matter of working through those 90 scores and indicating for yourself how frequently each of those 90 scores occurred. The second thing that you needed to do then was to compute a proportion. And that proportion was the proportion of the 90 residents who had received less than 1 visit per month on average. And we decided that in order to receive less than 1 visit per month on average, the individual would needed to have received fewer than 12 visits for the entire year. So what you needed to do was to add together, if we can look at the frequency distribution again, you needed to add together the frequencies associated with the scores of less than 11. That is, you needed to add together the scores associated with 0 visits, 1 visit, 2 visits, 3 visits, 6, 7, 8, 9, and 10 visits. That is, you needed to add 6, 2, 1, 1, 2, 1, 1, 1, and 1. And when you do that, you discover that that the resulting proportion, because you have to divide by the total number of scores, which is 90, the resulting proportion is 16 divided by 90, which is 0.178. Are there any questions regarding either the construction of the frequency distribution or the computation of the relevant proportion? If not, then let's pass on to the percentage, the notion of percentage. You were required, third, to generate the percentage of residents who had received on average less than 1 visit per month. That is, you simply needed to transform the proportion, which was 0.178, into a percentage. So you multiply, and the percentage is the proportion P multiplied by 100. 0.178 multiplied by 100 is 17.8. That is, the percentage of the 90 residents who received, on average, less than 1 visit per month is 17.8. Are there any questions about the computation of the percentage? Then finally, you were required to compute the ratio, which is F1 divided by F2, the ratio of where F1 was the number of persons who had received, on average, less than 1 visit per month, and F2 was the number of persons who had received at least 1 visit a month. Well, you've already computed the number of people who received less than 1 visit a month. That was 16. So that the number of people who received at least one visit per month is the total 90 minus 16, which is 16 divided by 74, which is 0.216. Are there any questions about any of this material? That is, are there any questions dealing with the construction of frequency distributions or the computation of proportions, percentages, or ratios? Hearing none, we go on. As I've indicated to you, this information, both the answers and the process that leads to the answers, computational process, are available now on WebCT for you. And if you're at all uncertain, you can simply check there. Yeah.
Is the percentage always going to be the proportion multiplied by 100?
Yes. The question is the percentage always going to be the proportion multiplied by 100? And the answer is yes. You're simply putting a proportion on a different scale. Are there any questions? Let's talk then about measures of central tendency. Let me first of all make a couple of observations, first of all about the nature of research, and then about notation. Researchers quite clearly, and I presume this is familiar to you, but researchers quite clearly are interested in populations of people. At least you and I in communication are interested in populations of people. Whether those people are all people who watch TV, whether they are children under the age of 7 who watch a certain kind of television or a certain kind of or television at a certain period of time, whether it's persons who stutter when they talk, whether it's persons who read a local newspaper, whether it's persons with a blood pressure above some level, whether it's persons who are registered to vote, and so forth. Researchers are concerned with populations of people. Almost invariably, those populations are inaccessible. That is, those populations are unavailable to the researcher. Clearly, it makes little sense to imagine that you could examine every child under the age of 7 who watched a certain type of programming or programming at a certain time. Clearly, it's unreasonable to expect that you could test, examine, observe all persons who stutter. Clearly, it's unreasonable to suppose that medical researchers can examine all people with a blood pressure above some level. That does not mean, however, that researchers are not interested in populations of people. They are acutely interested in populations of people. What they have available to them, however, is samples of those populations. That is, some subset of persons who stutter, some subset of all children under the age of 7 who watch a particular type of television programming, some subset of people with elevated blood pressure, some subset of registered voters. Nobody cares about that subset, only in as much as it informs you and I about populations as a whole. Nobody cares about the 124 persons with elevated blood pressure who participated in the study at Baylor University, except to the extent that that informs you and I about all people with elevated blood pressure. all people perhaps within some limited domain, all people in the United States, all people in Houston, all people in Texas, but some population. The book at this point starts to use, Healy starts to use a standard set of notations, and I want to simply move through that notational system. It's not something that requires any explanation. It's simply something I think that we need to look at, sort of commit to memory and become familiar with. We can distinguish then between a sample and a population. And as we move through this chapter, we will talk about mean scores. Mean is simply another word for average. We will also, when we talk about measures of central tendency, we need to move over here a little bit. When we talk about measures of central tendency, we will talk about something called standard deviation. Standard deviation. And we will also talk about something called variance. Now there is a standard set of notation for that denotes each of these parameters. A sample mean is represented by uppercase X with a slash over it. Uppercase X with a slash over it, referred to as X bar. X bar. Now I have to tell you that my computer does not have, at least nowhere that I can find, has the symbol X bar loaded in there. And so we will use in class an alternate symbol for sample mean, and that is uppercase M. Uppercase M. But both uppercase M and X bar denote sample mean. Population mean is denoted by the Greek letter mu. Sample standard deviation is denoted by lowercase s, and sample variance by lowercase s squared. Population standard deviation is denoted by the Greek letter sigma, and variance by sigma squared. All of this is, of course, in the text, but it's important. It will become more important when we look at measures of variability to distinguish between samples and populations. So sample mean is represented by uppercase X with a slash over it, X bar. We will use capital uppercase M. Sample standard deviation is represented by lowercase s and variance by lowercase s squared. The population mean by the Greek letter mu. Population standard deviation by sigma, and population variance by sigma squared. I don't think this is an issue that requires any discussion. It's not a conceptual issue. It's simply a system of notation. Let's then talk about measures of central tendency. There are three. The first is the mean. Mean is simply another word for average. And most of you, all of you I presume, are familiar with the notion of a mean or average. In order to compute the mean, the formula for computation is the sum of xi over n. Now that may be a little unfamiliar to you, but the process that it denotes, I think, is very straightforward and very familiar to you. The sum of xi over n simply tells you to add together, to sum together all of the individual scores and then divide by n the total number of scores. And if I were to ask you to compute the mean of the 90 scores on page 37, that is the 90 scores that you use to construct a frequency distribution and so forth, I suspect that each of you would add 0 to 52 to 21 to 20 to 21 and so on and so on. That is, you would add each of the 90 scores together. You would sum together all of the xi's, and then you would divide by n the number of scores. And if you did that, I believe you would discover that the answer was 24.4. I believe it's 2,198 divided by 90, which is 24.4. I would be absolutely certain had I not left the materials in a previous classroom. But this is, I presume, a process that's very familiar to you. Are there any questions on computation of the mean? You can compute the mean in another way. That is, you can compute the mean directly from the frequency distribution. And if you do that, the mean equals the sum of fxi divided by the sum of f. The sum of fxi divided by the sum of f. If you recall, on the frequency distribution, the frequency distribution that describes the data set on page 37, you had two columns, one headed xi and one headed f. You discovered that the number 0 occurred 6 times in the 90 scores. You discovered that the number 1 occurred twice, and so on and so on. The denominator here, then, the sum of f, is straightforward. It's simply the sum of the frequency column. That is 6 plus 2 plus those numbers below it, which was 90. Yes, there were 90 scores. Are there any questions about the denominator here, the sum of f? Yes.
So the second formula is to compute what, did you say?
The question here is, what am I computing? I'm computing the mean, or average, just as we computed the mean using this formula, which says add together all of the individual scores, the xi's, and divide by n. We can also compute the mean directly from a frequency distribution. So this is simply a formula for the computation of the mean, but using the language, the notation of the frequency distribution. The sum of fxi divided by the sum of f. Well, I've tried to point out to you that the sum of f is familiar to you. It's something you used when computing proportions and percentages and ratios in the exercises that you did last week. The sum of F is simply the sum of the scores in the frequency column. That is, it's the total number of scores, 90. But you do not have an FXI column. What you have to do is then generate that FXI column simply by multiplying the individual scores, the XIs, by the frequency with which those individual scores occur. So 0 times 6 is 0, 1 times 2 is 2, and so on through the frequency distribution. Now, in order then to generate the numerator here, which I think is 2,198, you simply add together the scores in the FXI column. 0 plus 2 plus whatever scores there are beneath that down through the entire frequency distribution. While I have used the notion of multiplication, you understand that multiplication and addition are functionally the same. That is, to multiply xi by f is functionally equivalent to adding together the 6 zeros. Would you agree? And multiplying 1 by the frequency with which it occurs twice is functionally equivalent to adding together the 2 ones in the distribution. So while we've talked about this notion of fxi in multiplicative terms, it's functionally the same as addition, which is precisely what we did when using the base formula for the computation of a mean. We added together all of the individual scores. I want you to understand that when you sum together fxi, that is, when you generate the fxi column and you sum those scores together, all you're doing is summing together the xi's. But you're doing it in 2 steps. The first step is to add together all of the scores that are the same. That is, you add together all the zeros, you add together all the 1s, you add together all the 2s, all the 3s, through to adding together all the 52s. The second step is then to add together those scores. And once again, the mean or average of these scores is 24.4. That is, the average number of visits received by the 90 residents was 24.4. Are there any questions about computation of mean?
So when you add together all the scores in fxi, you get what? The mean? The same thing?
When you add together fxi, you generate the numerator in the computation of the mean. That is, you generate what previously was labeled the sum of xi. You've simply functionally added together all 90 scores in this case. Yes. No, you need to press and hold.
Is it absolutely necessary to know how to do both formulas as long as we understand the first one?
Is it absolutely necessary to know both formulas? I was asked the same question in another class in a different way, which was, does it matter how we do it on the exam? It doesn't matter how you do it on the exam. What you should understand is that if you're dealing with a few scores, if you're dealing not with 90 scores, but let's say with 10 original scores, it probably doesn't matter whether you add those 10 scores together and divide by 10, or whether you construct a frequency distribution and compute the mean in this alternative way. But the more scores that you're dealing with, the more efficient is the second method. If you're dealing with 2,000 scores, it's very much quicker, very much more efficient to generate the frequency distribution and then use the second formula than it is to simply have to keystroke those 2,000 scores into your calculator. I don't think there's anything... So the answer to your question is it doesn't matter which of these formulae you use, which method you use on an exam to compute the mean. It is important, perhaps, to understand that the more scores you're dealing with, the more efficient is the second method relative to the first. Yes.
I don't understand how you get the same answer when you multiply, when you do the first way, just xi over n.
Let me deal not with those 90 scores. Let me deal with 5 scores. 0, 2, 2, 5, and 7. Yes? Here's method 1. Method 1, to compute the mean. And we could, it doesn't matter whether we're computing the sample mean, x bar, or population mean, mu. We could add together, we could sum xi and divide by n, which equals 0 plus 2 plus 2 plus 5 plus 7 divided by 5. Would you agree? Which equals 2, 4, 9, 16 divided by 5, which equals 3.2. Yes, 3 1/5. Would everybody agree? The second method, where we first construct the frequency distribution. Well, here are the xi's and here's f. Here, the xi's are 0, 2, 5, and 7. There is 1 0, there are 2 2's, there is 1 5, and there is 1 7. Yes? So that there are, in fact, 1, 2, 3, 4, 5 scores. We now generate the fxi column. 1 times 0 is 0. 2 times 2 is 4. And I will say again, that is functionally the same as adding those 2 2's together. 1 times 5 is 5, and 1 times 7 is 7. If we now add together the fxi scores, that is, if we generate the sum of fxi, 0, 4, 9, 16, which is the numerator back here, so that the mean here is the sum of fxi, which equals 16, divided by the sum of f. The sum of the f column is 5. So once again, the mean is 16 over 5, or 3.2. And as I've indicated, obviously, the more scores you're dealing with, the more efficient, the more relatively efficient it becomes to use this second method. Are there any other questions?
I think it's a lot more helpful when you show the example. If you do that more, that would be fantastic for me.
It would be fantastic. Well, one can hardly turn down fantastic. So we'll try to make this more straightforward. I will do that for you if you will do this for me. One of the cars I own is a Mazda Miata. And usually my wife drives it, but today I was forced to drive it into work. And I'm coming down the East Texas Freeway. I guess this is being recorded, so I should say I'm coming down the East Texas Freeway abiding by the speed limit. If the speed limit were 85 miles an hour. But we're all doing that in the outside lane. Behind me, and I mean on a Mazda Miata, the trunk is about this long. So about this far behind me is, behind my head, is a Chevy Suburban. Let me ask you a favor, because it'll improve your day and it'll improve the day of people like me. If you're following a Mazda Miata in particular, or one of those little tiny little cars in general, particularly if you're driving one of those tanks, or an 18-wheeler, you know, a Tahoe, a Suburban, whatever it is, back off. Back off. Because if anything happens, you're going to take that person's head off. You're going to take the head of the Miata driver's head. You're going to take that person's head right off. And that will spoil that person's day. And it will spoil your day too. So I will do that for you. If for me, if you're out there on the freeway, just when you see one of those little cars, back off just a bit, okay? It's a deal. We got a deal going here. The second measure of central tendency discussed in the text is the mode. The mode. The mode. The mode is simply that score or those scores that occur most frequently in a distribution. The mode is simply that score or those scores that occur most frequently in a distribution. If you refer to the frequency distributions that you generated for those 90 scores in the text, you will discover that there are in fact two modes. They are the scores of 12 and 50. So we have a mean of 24.4 and we have a bimodal distribution, that is a distribution, a set of scores with two modes, and those modes are 12 and 50, each of which occurs 7 times in the set of 90 scores. So while a set of scores can have only one mean, it can have multiple modes. A distribution or a set of scores with one mode is unimodal. If it has two modes, it's bimodal. If it has 3 modes, it's trimodal, and so on and so on. But the mode is simply that score or those scores that occur most often in the data set. And as I've indicated, if we rely on the frequency distribution, the data, and that is the data set from page 37 in the text that refers to those 90 residents of a retirement community, all you have to do is scan the F column, the frequency column, and look for the highest scores. And you'll find that the highest score is 7, and it occurs twice. If we refer back to the example that we were using previously when computing the mean, we generated our frequency distribution here. The most frequent or common score in the set occurs twice, and that is the number 2. So in this instance, the mode would be 2. It would be a unimodal distribution, and that mode would be 2. Are there any questions regarding the mode? The last measure of central tendency discussed in the text is the median. And the median is that score that divides the distribution in half, such that half of the scores are higher than the median and half of the scores are lower than the median. The median is that score that separates the distribution in half, so that half of the scores, 50% of the scores, are higher than the distribution, than the median rather, and 50% are lower. If we think again of the data set on page 37, that is the 90 scores pertaining to the residents of the retirement community. Would you agree that since there are 90 scores, the median is somewhere between the 45th highest score and the 46th highest score? In fact, it should be equidistant from the 45th and 46th highest score. Because then you will have, in a set of 90 scores, you'll have 45 scores below the median, and you will have 45 scores above the median. If you go back to the frequency distributions that each of you generated then for those 90 scores and search for the 45th and 46th highest, what you'll find is that the 45th highest score is 23, the 46th highest score is 23, and in fact the 47th highest score is 23. So that the median is somewhere between the 45th high, it's halfway between the 45th highest score, which is 23, and the 46th highest score, which is 23, so that in that data set, that is, for those 90 scores, the median equals 23. This is often the case with the median. You cannot find the theoretical median. That is, you cannot generate a score that separates the distribution in half in a precise way. In this instance, there is no score that separates the distribution such that 45 scores have a value higher than the median and 45 scores have a value lower than the median. If we were to deal with a different set of scores, 0, 5, 7, 9, and 12. We have 5 scores. Would you agree that the median would be the third highest score? Because under those circumstances, if we found the third highest score, we would have 2 scores with a value lower than the median and 2 scores with a value higher than the median. In this instance, then, the median is the third highest score, which is 7. In that instance, you would have 2 scores lower than 7 and 2 scores higher than 7. If we had, in fact, 6 scores in this distribution, would you agree that the median would be somewhere between the third highest and the fourth highest? In fact, it would be halfway between the third and fourth highest. The third highest score here is 7. The fourth highest score is 9. The median then would be halfway between those 2 scores. The median would be 8. Yes. Yes.
What if the number was the same? Like there would be 2 7s. Would it just be 7?
Then if rather than 0, 5, 7, 9, 12, 14, we had 0, 5, 7, 7, 12, and 14. We would be in the same situation as with the data set from the text, and that is the third highest score would be 7, the fourth highest score would be 7, and the median would be 7. And again, as I've indicated, as is often the case, we would be unable, there would be no score that would divide the distribution precisely in half. Yes.
So on the frequency distribution chart, were you looking at XI or F to find the median?
You would look
to find the median.
To find the median. You would look at the frequency scores because you're interested not in the individual scores as such. Let's go back a moment to our very simple example. In order to locate, for example, the median of these 5 scores, we would want a score somewhere between the second and third highest. Would you agree? Well, this doesn't show. Let's go through the process. The highest score is here. Yes, regardless what that score is. Let's forget what the individual scores are. The highest score is this one here, right? With the check mark next to it. The second highest score is this score. So the third highest score is one of these 2 scores here. Would you agree? Yes? Whatever those scores are, because there are 5 scores, so the median is somewhere between, the median is the third score.
So it doesn't matter which ones are actually highest?
Let's get through this. Let me work my way through it. I'm about as muddle-headed as a person could be at the moment. If we have 5 scores, we're looking for, and I think I said somewhere between the second and third. In fact, we're looking for the third highest score. Because if we, in a set of 5 scores, the third highest score will then have 2 scores with a value lower than it, and 2 scores with a value higher than it. Now, forget what these numbers are. Forget the XIs. Here's the highest score, whatever it is, next to it here. This indicates the second highest score, so that the third highest score is one of these 2 numbers here. And now we look across and we find that those scores are 2, so that the median is somewhere between 2 and 2, which would be 2. The third highest score here is 2. That doesn't seem to have satisfied you. What I've tried to do here is, you asked, are you looking down the XI column, at the individual scores, or the frequency column, the F score at the frequencies? Well, you're looking at the frequencies preliminarily, because you're looking for the third highest score, or the 45th highest score, or the 19th highest score, whatever it is. So you're looking here to count to 19, or 45, or 3. But at that point, what you're interested in is what that score is. So you're interested not in the frequency with which it occurs. You're interested in the score itself. So my answer to you is you're interested in both. You're looking first at the set of frequency data, and then you're looking at the individual score. Are there any other questions? Now that I've confused everybody with that.
Would it be correct to say that you don't really have to look at either column, you can just look at your set of numbers?
no, you can't look at the set of numbers unless you arrange those numbers from highest to lowest or lowest to highest.
Right. Wouldn't that be the easiest way?
Well, I don't think so. Let's take the 90 scores on page 37. To compute the median as you suggest, what we would have to do is arrange those scores from lowest to highest. That is, we'd have to write out the 90 scores from lowest to highest, which seems to me would be an arduous task. And then we could count up there. You're doing precisely the same if you generate a frequency distribution, except you're listing those 90 scores in an abbreviated or summarized way. Are there any other questions? Yes.
Where would we use this in real life?
Where would you use this in real life? If you were to generate a very large set of data that you could then roll up into a ball, you might use it in a restaurant when a child runs through the tables, or in a movie when somebody talks. You could actually throw it at them. It might have some. I'll talk about real-world value in a minute. And I want you to know that those are some rules of life. Never take a child to a restaurant where the child cannot order from a board on the wall. If the child has to order from a menu, the child doesn't belong there. Never take a child to a movie that begins after 1 o'clock in the afternoon. And never get so old and go to a movie that you can't follow the plot and you have to ask the person next to you. All of those things happened to me over the weekend. Where do you use this in real life? We talked about data reduction. That's a sort of general theme here. We talked preliminarily about frequency distributions, which really don't serve to reduce the data set. It simply reorganizes the data set in a more coherent way. That is, in a way that is more coherent than the original set of scores. The frequency distributions that each of you constructed based upon those 90 scores in the text was more coherent, more informative, more readily understandable than were the 90 individual scores. But we still had 90 individual scores. That is, we were doing very poorly in terms of efficiency, but very well in terms of retaining as much of the original information as possible. And recall, when I talked about data reduction, I said it was invariably involved a trade-off between those two things, between the efficiency of the indicator, which here was a frequency distribution, and retention of original information. What we've done now is to go very much further than that. We have, in two instances here, represented this entire data set with a single score. The mean, 24.4, and the median, 23. And in the other instance, we've represented the entire data set by two scores, 12 and 50, when we were looking for the mode. What we've done then is to find ways of summarizing, of reducing a data set that are extremely efficient. You cannot become more efficient than using a single number to reflect 90 scores or 150 scores or 10,000 scores. The question now is, how are we doing on the other criterion? That is, to what extent do mean, mode, and median retain the original information? Another way of asking that question is, which of these measures of central tendency is the best one? And this isn't a rhetorical question. And we're going to stay here until somebody gets this right. This is going to be like eating your Brussels sprouts. Which of these measures of central tendency is best?
The very first one?
Mean?
Yes.
Remembering to press and hold, why is the mean preferred over the other two?
I'd say it would just be more accurate because it's more of an average. The other one sometimes, I don't know, it sometimes seems like since you're looking for the middle number, it wouldn't be as accurate because you didn't really put all of the information into it like you did for the first one. Does that make sense?
No, it makes sense eventually to me. That was sort of like a lot of geese take off. And you've got 2 or 3 shotguns. Boom! And eventually you hit the goose that you were looking for. The goose that you were looking for was the comment you made about all of the information. When you compute a mean or average, you have to add together all of the individual scores. And you have to divide by the total number of scores. That is, the mean is sensitive to all of the original information. That is not the case with either the mode or the median. To identify the mode, you simply scan the frequency column looking for that score or those scores that occur most often. In order to compute or identify the median, you simply look for that 50th percentile score. And it doesn't matter what the scores around it are. So the mean is the preferred measure of central tendency, usually, because it is sensitive to all of the original information. And so should provide, typically does provide, is a better descriptor of the data set as a whole than are the alternatives. There is a circumstance under which that is not the case. For example, when you hear reported to you data associated with annual income, annual family income, typically you do not, that information is not provided in the form of an average or mean score. We don't talk typically about average family income. We talk instead about median family income. To eventually answer your question, where does this appear in the real world? At least one place is here. We typically talk about median family income and not mean family income. Why is that the case?
Because the distribution is there's a big gap between the people that make a lot and the people that make a little. So the average wouldn't be right.
Yeah, you're getting there. You're getting there. You've identified the source of the problem with income data. That is, there are a few people who earn a lot. There are people who earn. There are people who throw a baseball with their left hand who have a season record of 10 wins and 14 losses, and they're earning somehow $15 million a year. Yeah. If they're seventh man on a basketball team and pull down 2 rebounds and score 3 points on average a game, they're earning even more. They're earning $15 million a year. Some people who stole from Enron, were employed by Enron, took home $258 million a year. That's part of the problem. Part of the problem is you have these few extreme scores. But the real problem is not simply that you have these few extreme scores, they're all at the same end of the distribution. There is no negative analog to $7 million a year, or $15 million a year, or $258 million a year. You can't earn less than zero. So the problem, the mean, becomes misleading in a circumstance where there are a few extreme scores at one end of the distribution, as is the case with family income. What happens in those... the issue of extreme scores is not in and of itself problematic. If you have extreme positive scores and extreme negative scores, they sort of cancel themselves out in their effect on the mean, and the mean still does usually a good job of describing the set as a whole. The problem when you have extreme scores at only one end of the distribution is that those extreme scores exert an undue influence on the mean because they pull the mean towards them. So that the mean no longer describes the bulk of scores in a very good way, because it's been unduly influenced by these few uncharacteristic extreme scores. And in that instance, as I've indicated, researchers usually rely upon the median. Let me just go through parts, the issues that you need to come to grips with. One, how to compute mean, mode, and median, and what each is. And finally, the sort of strengths and weaknesses of each of those three. And it has to do with ability to retain original information and the effects of extreme scores at one end of the distribution. There are no problems that are assigned for this chapter by itself. What you need to do to prepare for next time is to read the chapter, read the material dealing with measures of variability. And we will then, I will then make available sample problems that you will discover involve some of the issues that we've discussed today, as well as the issues dealing with variability. Are there any questions? No? Then I will see you next time.